Hello and welcome to EPG Pathshala. This module provides an overview of Bradford distributions. The objectives of this module are derivation of equations for Bradford distribution by various bibliometricians, viewpoints of some bibliometricians on the law, discussion on ambiguity between verbal and graphical representations of Bradford distribution, discussion on Bradford-Ziff distribution, and characteristics of bibliometric distribution. In this module, titled Classical Laws of Bibliometrics, we have discussed Bradford's law of scattering and its definition, explanation, derivation, verification, uses, among others. A great deal of work has been done with this law. An attempt is made in this module, Unit 6, to highlight some of the related works. Cole's formulation. Cole experimented with Bradford law and named the slope of the curve as the reference scattering coefficient and concluded that the coefficient might be the characteristic of the subject field. For petroleum literature, Cole obtained the following relationship. Function of x is equal to 1 plus b log 10 x, where x is greater than c. Here, function of x stands for the cumulative number of papers contained in the x number of most productive journals, and c represents the number of journals figuring in the nuclear zone. For petroleum literature, Cole found the value of b as 0.43. Limecouller's formulation. Ferdinand F. Limecoller, professor of industrial engineering of the Purdue University of the United States, analyzed all the published data on Bradford distribution and derived the following equation for Bradford distribution applying statistical techniques. Function x is equal to log 1 plus beta x divided by log 1 plus beta, where 0 is less than or equal to x, which is less than or equal to 1. In the equation, function x stands for the cumulative fraction of the references, x for the corresponding fraction of the most productive journals, and beta is a constant related to the document collection. Brooks opined that the equation is but a compromise since Limecoller accepted the empirical data as both complete and exact. Brooks further observed that, unfortunately, though Limecouller's formulation can be used theoretically without difficulty, it has some disadvantages for the practical documentalist. The numerical evaluation of the key parameter beta requires tedious statistical computation and the solving of an implicit equation by approximation methods. Brooks formulation. Two formulations by Brooks are given below with the explanation of each component of the formulation. Rn is equal to k log n, where Rn is the cumulative total of relevant papers found in the first n journals. N is the number of journals, k is the constant. Rn is the cumulative total of relevant papers found in the first n journals. Capital N is the total number of periodicals expected to publish paper on the subject. Small n is the number of journals. S is the value of n at the intersection of the straight portion of the curve with the x-axis. And C is the value of n at the point where the straight portion of the curve begins. Bradford considered the bibliograph to be a straight line, which has resulted in two different formulations. One is verbal and the other is graphical. The algebraic expressions for the two formulations given by Brooks are Rn is equal to j log n divided by t plus 1 for the verbal formulation, and Rn is equal to k log n divided by s for the graphical formulation. Naranan's point of view. In 1970, Naranan opined that Bradford's law of bibliography of scientific literature is explainable in terms of an underlying power law distribution of the number of articles in scientific journals. The law emerges as a natural consequence of exponential growth of scientific literature and journals at comparable rates. And thirdly, a model like this predicts a strong correlation between the age of a journal and the number of articles it carries. The author was hopeful that the proposed mechanism might find wider application in many other fields of science. Brooks pointed out that Naranan's analysis was not valid for Bradford. Hubert was of the view that Naranan interpretation of the original form of Bradford's law does not follow a stochastic argument based on his assumptions. However, his paper provided a plausible model of Lotka's law with suitable verbal amendments. The comments of Brooks on the paper are being reproduced verbatim. He says, "The inverse square law of scientific authorship has hitherto been regarded as an inexplicable and useless scientific oddity. Naranan's model of it is therefore welcome, and together with other measures of scientific productivity, Lotka's law has recently been applied by Dobrov and Korenoi in determining the optimum size of research institutes in USSR." Bookstein's viewpoint. In his paper published in 1976, Bookstein analyzed the distributions of Lotka, Ziff, Bradford, and Limecoller and adopted a point of view that allows us to understand that these distributions are in fact the different versions of a single theoretic distribution. He generalized these distributions with the following words: "All of these distributions are almost equivalent. In each case, we have a set of entities, for example, chemists, words, who produce events, publications or occurrences, over some dimension of extension, a time or a length of text. And in each case, the distribution describes the number of occurrences of events over a fixed interval of that dimension. Under these conditions, it is possible to describe the same distribution in at least 4 distinct ways. These modes of description are represented above by the distributions of Lotka, Ziff, Bradford, and Limecoller." Bradford multiplier. The number of periodicals in the 3 zones of Bradford distribution generally follows the ratio 1 is to n is to n to the power 2, where n is the Bradford multiplier. Ravichandra Rao analyzed the Bradford multiplier with a small sample of 12 data sets using the t-test. An attempt has also been made to identify a suitable model to explain the law of scattering. Among the various methods tried, log normal fits much better than many models, including the log linear model. Ambiguity between verbal and graphical statements. Bradford expressed his law in 2 different ways, graphically and verbally, resulting in 2 formulations. The verbal formulation is n to the base m is to n to the base 2m minus n to the base m is to n to the base 3m minus n to the base 2m, so on up to 1 is to a to the base m is to a to the base m to the power 2. The graphical formulation is equivalent to the expression n to the base m is to n 2 to the base m is to n 3 to the base m, so on up to 1 is to b to the base m is to b to the base m to the power 2, where n to the base m signifies the number of journals in the first zone contributing m number of papers. N to the base 2m signifies the number of journals of the second zone contributing m number of papers. N to the base 3m signifies number of journals of the third zone also contributing m number of papers. AM and BM signify Bradford multiplier. This apart, when the graph is plotted with the data of verbal formulation, it takes a different shape compared to the shape of the graph with complete data set. In table 2, you can see the distribution of articles according to zones. In the first zone, there are 10 periodicals and the cumulative number of articles is 445. In the second zone, the number of periodicals is 49 and the cumulative number of articles is 886. And in the third zone, the number of periodicals is 267 and the cumulative number of articles is 1332. Also, you will find that the y-axis stands for the cumulative number of periodicals and the x-axis for the cumulative number of articles. Figure 2. Bradford's bibliograph with verbal formulation. When the graph is drawn with the entire data set, we find finer details which are lost in the graph of verbal formulation. Now let us see the graph with the entire data of table 1. Figure 3. Bradford's bibliograph with complete data. In this figure, y-axis stands for cumulative number of periodicals and x-axis stands for cumulative number of articles. Slide 14. Comparing the two bibliographs, we find the following. In the verbal formulation, the entire data is not available. What we get is practically a summary of the entire data set. The bibliograph in figure 2 is incomplete inasmuch as it does not indicate the starting point of the curve. The last portion of the graph in both figures 2 and 3 is a straight line. In the graphical presentation of some Bradford distributions, a droop is observed at the end of the graph which is not seen with the data of verbal formulation. With these, the distinction between verbal formulation and the graphical presentation becomes quite clear, and the shortcomings of the verbal formulation become apparent. Brooks has provided equations both for verbal formulation as well as graphical formulation. The equations are given under Brooks formulation. Bradford-Ziff distribution. M.G. Kendall, a statistician by profession, also studied Bradford distribution using 1,763 references on operational research pertaining to 370 journals. For the sake of comparison, 1465 references to statistical methodology covering the period 1925 to 1939 were used. The graph plotted following Bradford's method produced a curve which was remarkable for its linearity. He also noticed that the law is similar to but not identical with the Zipf's law. Let us consider the data given in Table 4. The data set provides the typical Bradford distribution. Table 4 consists of a data set following Bradford distribution. Inverting the columns 1 and 3 of Table 4 and multiplying the numbers of each row, we get the following result, as shown in Table 5. The number in the second column may be considered as frequency. Table 5 shows a partly inverted form of Table 4. The figures in the third column clearly indicate that they by and large follow Zipf's law. The two distributions are in fact very close. Hence they are often referred as Bradford-Zipf distribution. The linearity of the Bradford bibliograph indicates a true Zipf situation. Characteristics of bibliometric distribution. All bibliographic distributions can be expressed through algebraic expressions. On graphical presentation, they form different types of curves. All these distributions have given rise to well-established laws which have found applications in journal selection, ranking of authors, ranking of words for keyword generation, and so on. The classical laws of bibliometrics generally follow power law distribution. All these laws are basically different versions of a single bibliometrics distribution. The discussion above comprises mathematical formulation and views on Bradford distribution. Obviously, bibliometricians paid more attention to mathematical formulation rather than its use. Eugene Garfield is an exception. He used this law profitably for selecting journals for various editions of current contents, Science Citation Index, and other citation indexes. In the early 1960s, there was no reliable estimate of scientific periodicals being published in the world. The estimates varied from 50,000 to 1 lakh. From these, he was to choose initially 600 plus periodicals. In the 1970s, the number went above 2000. Here, he took the help of Bradford distribution and went for core periodicals of a specialty. In this process, he discovered that only about 10% of the periodicals are accounting for about 90% of the citations. This finding gave rise to the Garfield law of concentration, which is defined as follows. The list of journals most cited in any individual specialty is essentially the same for all specialties. A basic concentration of journals is the common core or nucleus of all fields. For building up a core collection of periodicals for a specialty, Garfield law of concentration is of great help.